Previously, we required that the population standard deviation be known. This assumption is unrealistic. In this chapter, we will estimate the population standard deviation by using the sample standard deviation. This leads to the introduction of a new distribution that must be used in such cases. It's called the t-distribution. So the concepts we'll be talking about in this chapter: the conditions for inference about a mean, the family of t-distributions, a one-sample t-confidence interval, the one-sample t-test, using technology, a matched pairs t-test, and the robustness of t-procedures. So, we rarely know what the standard deviation of a population is. So instead, we need to use the only other thing we have, and that's the sample standard deviation. And we use that in place of sigma. So let's review the conditions for inference about a mean. We required that the data come from a random sample from the population. We insisted that the population have a normal distribution. In practice, it is enough that the distribution be symmetric and single-peaked, unless the sample is very small. And we'll get a little more specific about that later. And we're going to have a new requirement, and that is independence. So the population must be much larger than the sample, say at least 20 times as large. So when the conditions for inference are satisfied, the sampling distribution for the mean has roughly a normal distribution. Because we don't know the standard deviation of the population, we estimate it by the sample standard deviation S, or S sub x. So the standard error of the sample mean is, as it's called, is the standard deviation of the sample divided by the square root of the sample size. And it does do pretty much what it did before. It describes how far a sample mean will be from the population mean on average in repeated random samples of a particular size. So when the sampling distribution of the mean is close to normal, we can find probabilities involving the mean by standardizing. We used the z-score. Z equals the mean minus the sample mean minus the population mean over the standard deviation divided by the square root of the sample size. And we had values of x, and the standardized scores had a mean of 0 with a standard deviation of 1. Okay, when we don't know sigma, we can estimate it using the sample standard deviation. What happens when we standardize? Well, here we're saying what is x bar minus the hypothesized mean divided by the sample standard deviation over the square root of n. It turns out this new statistic does not have a normal distribution, like we'd like. Adjust a little bit. So when we standardize based on the sample standard deviation, the new statistic has a distribution called a t-distribution. It has a different shape than the standard normal curve. There are many similarities. It is symmetric with a single peak at 0. But it does have much more area in the tails. Like any standardized statistic, t tells us how far a sample mean is from the mean of the population in terms of standard deviation units. But there's a different t-distribution for each sample size, and this is specified by what's known as its degrees of freedom, and we abbreviate that df. When we perform inference about a population mean using a t-distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size. So df equals n minus 1. That changes depending on the type of a test, but for now it's just n minus 1. So if we draw a simple random sample of size n from a large population that has a normal distribution with a mean mu and standard deviation sigma, the one sample t statistic given by the formula does have this t-distribution with degrees of freedom n-1. So let's take a look at comparing some of the density curves of the t-distribution. So in this case, notice that the purple line here is the standard normal curve. The dotted red line shows the t-distribution with 2 degrees of freedom. Notice it's fatter in the tails than the normal distribution. And the light blue curve is the t-distribution for 9 degrees of freedom. Still a little bit fatter in the curves, in the tails. So that does affect the probabilities. So the density curves are similar in shape, but the spread of the distributions is greater than that of the standard normal distribution. The t-distributions have more probability in the tails and less in the center. As the degrees of freedom increase, the t-density curves approach the standard normal curve. So the larger the sample size, the closer to the normal distribution these t-scores distributions are. So we'll use Table C in the back of the book to determine critical values with degrees of freedom. So, using Table C, suppose we want to construct a 95% confidence interval for the mean of a normal population based on a simple random sample of size 12. What critical t-value should we use? Remember when we used z-scores to do this, it was fairly simple. The 95% confidence interval, the z-star was 1.96. Here things change a little bit. So we take a look at Table C. Notice on the left the degrees of freedom are given, and then across the top row is the confidence level. So first we locate the row corresponding to the degrees of freedom in our case. So the sample size is 12, degrees of freedom are 11. Next we move across to the column directly above the 95% confidence level. And where those two overlap, that's our critical t-value. So the desired critical value is t star equals 2.201. Notice that's bigger than 1.96 we used before. So a one sample t confidence interval for a population mean is similar in reasoning and computational detail to the one we use for the one sample z interval. We choose the simple random sample, and the confidence interval for the mean is pretty much the same formula. It's the mean, x bar, of the sample, plus or minus the critical t-value, times the standard deviation of the sample, divided by the square root of the sample size. And we need to be careful. We only use this interval when the population distribution is normal or when the sample size is large, and let's say when n is greater than or equal to 40. And also the population needs to be at least 20 times as large as the sample. So let's do an example. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. The tension is measured by an electrical device with output readings in millivolts. A random sample of 20 screens has the following mean and standard deviation. So the x bar is 306.32 millivolts, and the standard deviation for the sample is 36.21 millivolts. So, using the four-step process, we want to estimate the true mean tension of all video terminals produced this day, and let's say at a 90% confidence interval. So if the conditions are met, we can use a one-sample t-interval to estimate the mean. So is it random? We're told that the data come from a random sample of 20 screens. So yes. Is it normal? Since the sample size is small, less than 30, we must check whether it's reasonable to believe that the population distribution is normal. since we don't know what the population distribution is, we actually need to use the sample to give us a sense of whether it's normal or not. So here we have 3 different plots. A dot plot of the information, a box plot, and a normal plot. Now the box plot is fairly symmetric. That's probably the best obvious indicator. The screen tension dot plot, there aren't any outliers. There's no reason to believe that it's not a normal distribution. And the normal plot is fairly linear. So these graphs don't give us any reason to doubt that the population is normal. Independent. Because we are sampling without replacement, we must assume that at least 20 times the sample size, 20, there are 400 video terminals produced this day. So we're just going to assume that's the case. So we are told that the mean and the standard deviation are 306.32 and 36.21 respectively. Since n equals 20, we use the t-distribution with degrees of freedom 19. So we look at the table, table C, locate row 19, degrees of freedom 19, and then the 90% confidence level, and we find that the critical t-value is 1.729. Therefore, the 90% confidence interval for the mean is x bar plus, well, you can see the formula. So we plug in the numbers. That's 306.32 plus or minus the critical t-value, 1.729 times 36.21 divided by the square root of 20. And we get an interval. So we are 90% confident that the interval from 292.32 to 320.32 millivolts captures the true mean tension in the entire batch of video terminals produced that day. Okay, another example. The composition of the Earth's atmosphere may have changed over time. To try to discover the nature of the atmosphere long ago, we can examine the gas in bubbles inside ancient amber. Amber is tree resin that has hardened and been trapped in a rock. Remember Jurassic Park? The gas in the bubbles within the amber should be a sample of the atmosphere at the time the amber was formed. We will assume that the 9 observations in this case form a simple random sample from the late Cretaceous era. The mean and the standard deviation are 59.59 and 6.26 respectively. So we want to estimate the true mean percentage, mu, of nitrogen in the ancient air with a 95% confidence interval. So if the conditions are met, we'll use a 1-sample t-interval. We are told that the data come from a simple random sample of 9. So randomness is okay. Since the sample size is small, we need to check whether it's reasonable to believe that the population distribution is normal. Once again, we need to examine the distribution of the sample. So it's pretty obvious that from the stem plot and the box plot that there's left skewness. But for such a small sample, the data are not unreasonably skewed. And more importantly, there are no outliers. So again, there's no reason to doubt that the population is normal. So independent? Well, in theory, there are infinitely many samples of air, so we consider each of these samples to be independent. That's a large number. So we take the mean of the sample and the standard deviation of the sample. We first need to locate the critical value, t. So with sample size 9, the degrees of freedom are 8. And we locate the row 8, degrees of freedom 8 from table C, and the intersection with the column of 95% confidence. So the critical value for t is 2.306. And then we can crank out the numbers and do the calculations, and we get a confidence interval. So we conclude we are 95% confident that the interval from 54.78 to 64.40% captures the true mean percentage of nitrogen in the late Cretaceous era. So just by way of comparison, present-day atmosphere is about 78% nitrogen. Quite a difference. Now we're going to talk about a one-sample t-test, and that's a hypothesis test. So we choose a simple random sample from a large population that contains some unknown mean, and we want to test the hypothesis that our mean equals some hypothesized value. And the t-statistic that we're calculating here, again, is very similar to the z-statistic we had before. It is the sample mean minus the hypothesized mean, same thing we had, divided by, in this case, the standard deviation of the sample over the square root of the sample size. And then we'll get a p-value in the same way that we had before, depending on whether it's a one-sided or a two-sided test, and so on. And again, we need to consider the degrees of freedom for each t-value that we look up. So the p-values are exact if the population distribution is normal and are fairly close for large and in other cases. So here's an example. The level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. So a researcher measures the dissolved oxygen level at 15 randomly chosen locations along a particular stream. And these are the results. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So we want to test whether the stream has dissolved oxygen levels below 5 or not. So the null hypothesis is that the mean level of dissolved oxygen in the stream is 5. The alternative is that it's less than 5. Okay. So again, if the conditions are met, we can do a one-sample t-test. So is it random? Yes. The researcher measured it at random locations. And again, we don't know whether the population distribution is normal at all points. And for such a small sample size, we need to look at the data to see if it's safe to use t procedures. So once again, here we have a histogram, a box plot, and a normal plot. The histogram looks roughly symmetric, the box plot shows no outliers, and the normal probability plot is fairly linear. So with no outliers or any strong skewness, the t procedure should be pretty accurate, even if the distribution is population. So we need to calculate the test statistic. So we plug in the values, and our calculated t-score, the test statistic, is minus 0.94. So the p-value, again, is the area to the left of t equals 0.94 under the t-distribution curve with 14 degrees of freedom. So the shaded area, much like it was with z-scores that we did before. So once again, we locate 14 degrees of freedom on table C, and in this case, we want to compare the absolute value of our test statistic with the given values of the critical values in table C. So here, 0.94 falls between 0.868 and 1.076 in the row with 14 degrees of freedom. So once again, we can estimate the p-value by looking at the bottom of the table where we have one-sided and two-sided p-scores. And in this case, the p-value falls between 0.15 and 0.20. And in this case, since it's greater than our alpha level at 0.05, we fail to reject the null hypothesis. So we don't have enough evidence to conclude that the mean dissolved oxygen level in the stream is less than 5 milligrams per liter. So keep in mind, since we decided not to reject the null hypothesis, we could have made a type 2 error. If we did, then the mean dissolved oxygen level is actually less than 5 milligrams per liter, but we didn't detect that with our significance test. So if that's important, you might need to do something, do some other kinds of testing. Okay, we've talked about matched pairs procedures before, and that's where we're looking at taking a measurement from a sample of individuals, people, or objects, or something like that, and then we take the same, we apply some kind of a condition on that sample, and then we take measurements of the same individuals at another time or something. And then we look at the difference between them. That's matched pairs. This is actually comparative studies. And these are usually more convincing than single sample investigations. So one sample inference is less common than comparative inference. But one sample is still used. So study designs that involve making 2 observations on the same individual, or 1 observation on each of 2 basically similar or identical individuals, results in what are called paired data. So when paired data result from measuring the same quantitative variable twice, as in the job satisfaction study we did, we can make comparisons by analyzing the differences in each pair. If the conditions for inference are met, we can use the one sample t procedures to perform inference about the mean difference. So for matched pairs t procedures, we compare the responses to the 2 treatments in a matched pairs design, find the difference between the responses within each pair, and then apply the one sample t procedure to these differences. So here's an example. Police trainees were seated in a darkened room. 10 license plates were projected on the screen, one at a time. The lights were turned on, and the police trainees were asked to write down as many of the 10 license plate numbers as possible, in any order at all. A random sample of 15 trainees who took this test were then given a week-long memory training course. Then they were retested. The results are shown in the table below. So, question, did the training improve their ability to identify license plates? So we want to perform a test at a 5% level of significance. The null hypothesis is that the mean is 0, that is, the difference of after and before is 0. And the alternative is that they improved, so the after result is greater than the before result. So the difference after minus before is greater than 0. And if we have the conditions, we can use a matched pairs t-test. So the researcher measured the ability to identify license plates for randomly chosen officers. That condition's met. We don't know whether the population distribution of differences is normal or not, so we need to take a look at the sample. So here we have a histogram of differences before minus after, a box plot, and a normal probability plot. And they look reasonably symmetric, no outliers, and the probability plot is fairly linear. So we're using t procedures. So the test statistic, keep in mind the x bar is the difference between after minus before, and we have a mean of 1.533, standard deviation of 2.2. So we plug those values into the formula, and we get a t statistic of 2.7. The p-value is the area to the right of 2.7 under the t-distribution curve. Remember, the alternative hypothesis was that it's greater. So in this case, again, we look at Table C, the row with 14 degrees of freedom, and the calculated test statistic 2.7 falls between 2.624 and 2.977 on the row with 14 degrees of freedom. We look down at the bottom to find the corresponding p-score, and the p-value is between 0.01 and 0.005. Since that's less than 0.05, we reject the null hypothesis. And we conclude there is evidence to suggest that the training will result in improvement in the ability to identify. Now, a confidence interval or significance test is called robust if the confidence interval or p-value does not change very much when the conditions for use of the procedure are violated. So the conditions such as skewness, outliers, that type of thing. So for general guidelines when using t-procedures, except in the case of small samples, the condition that the data are a simple random sample from the population is actually more important than the condition that the population distribution is normal. Again, unless it's a small sample. So for sample size less than 15, we need to ensure that the data appear close to normal, and in the case where the data are clearly skewed, or if there are any outliers present, do not use t-procedures. If the sample size is at least 15, then the t-procedures can be used except in the presence of outliers or strong skewness. So even in cases where it's skewed somewhat, but not terribly skewed, if the sample size is 15, we're okay. And then for large samples, based on the central limit theorem, we can use t-procedures for even clearly skewed distributions. That is, when the sample is roughly larger than 40. To review, we talked about describing the conditions necessary for inference. We described the t-distributions, check the conditions necessary for inference, construct and interpret a one-sample t-confidence interval, perform a one-sample t-test, perform a matched pairs t-test, and describe the robustness of the t-procedures.